everyone, and thank you for joining us again today. I'm really pleased today to welcome two of my colleagues from the Lincoln Institute of Agri-Food Technology, based up at our beautiful Ricehome campus. And we're really pleased that Ricehome has had a bit of a facelift recently, and look forward to welcoming visitors back there in due course. Isabel Wright is going to talk first. She's an agriculturalist focused on sustainable farming. She's passionate about making sure our food system in Lincolnshire is as sustainable and healthy as possible. Following her will be Professor Simon Pearson, who's the director of the Lincoln Institute of Agri-Food Technology, an expanding technology department, and I'm sure you're going to find out a little bit about all sorts of interesting things, including robots, in today's talk. He is very proud of his Lincolnshire roots, but is now a global leader in the development of agri-robotics. They are going to talk today on climate change, an opportunity to change practice for the Lincolnshire agriculture and food industry, and I'm very pleased to present them both to you. I'm sure you'll enjoy this.
Hello everybody, thank you for tuning in. I'm Isabel. I work for Simon Pearson at Ricehome, and in this slide you can just see an aerial photo of our farming campus. So we have an agricultural campus about 5 kilometres north of our main university campus. So just for the next 10 or 15 minutes, I'm going to introduce some of the complex aspects of climate change for agriculture and the huge opportunities that we have. I think it's a very exciting time for agriculture and food production in the face of climate change. And then we'll pass over to Simon. So just before focusing on climate change itself, I just wanted to show you this graph. So this graph shows the rate of population increase, the red line, and the total global population, a very familiar graph to you all, I'm quite sure, from 1700 up to 2100. We're about where the purple line is. No, we're about here at 7.7 billion. That was 2019 in the globe. Globally. I just had a quick look at what, if this forecast is right, what our population would look like just in 9 or 10 years' time. 8.5 billion compared to 7.7 billion, which is about a 10% increase. So somehow, with the same amount of land, but doing less damage to the planet, we have to achieve a 10% increase in food production. So that's quite a challenge. We've got to meet the needs of that growing population from food production. Combined with that, we have the climate crisis, which is impacting on our ability to produce crops, and the agricultural community is excuse me, I just read an instruction to remove that little button. The agricultural community is also adapting to climate change impacts that we're already seeing, and plus we have a biodiversity crisis, and it's really important that any changes we make in the future try to reverse the decline in biodiversity globally and locally that we have in biodiversity. And largely for Lincolnshire farmers and UK farmers, we have the impact on farming of phasing out EU support. So since Brexit, additional support for farming is slowly being phased out. Farmers are being given a few years to adapt. So that's the some of the background. Agriculture has this huge opportunity in the face of all these impacts, not just climate change. But let's move to climate change and agriculture. So the UK greenhouse gas emissions are only about 10% of the total greenhouse gas emissions, which is interesting. I think in the press you often hear that, or have the impression that our agricultural system is responsible for a lot of the greenhouse gas emissions, but it's only 10% of the whole, and the whole UK greenhouse gas emissions are about 1% of global greenhouse gas emissions. So it's actually quite a small proportion. Having said that, globally, if you look at both the food production and the whole food sector, so the agri-food sector, it's something more like 20 to 37%, so it is much, much higher. And if you look at those other industries, most of them are emitting carbon dioxide. Carbon dioxide is the principal greenhouse gas. It's much more complicated for agriculture. And it isn't just farming, is it? It's food production, and farming is linked to what we eat, what we import, and so on. So we're all involved in this. So let's have a look a bit more at that 10%. The greenhouse gases, if you joined Rebecca's talk a few weeks ago, she was talking about the fact that there are principally 6 gases responsible for global warming. Carbon dioxide is the most common one, then methane and nitrous oxide, and some other man-made gases. So these 3 are all measured, produced by agriculture, and have different impacts on global warming. So carbon dioxide is always given a global warming potential of 1, whereas methane has a larger global warming potential of about 25. We call that carbon dioxide equivalent. And nitrous oxide, a global warming potential of perhaps 300 times more than carbon dioxide. So we call that 300 times the global warming capacity of carbon dioxide in equivalents. So for the slides going forward, I talk about carbon dioxide equivalent. And I showed you before that most of the industries are producing carbon dioxide, and carbon dioxide is the most important greenhouse gas globally. It's not the same at all for agriculture. I also wanted to show you a couple of opportunities we have. One is this grey line with the arrow pointing to it. These are the greenhouse gas equivalent emissions, carbon dioxide equivalent emissions from agriculture from 1990 to 2018. And you can see actually that the agricultural line is flatlining really. So we have enormous potential to look at, can we reduce this? The UK government has a plan that we have net zero emissions by 2050. Actually, the agricultural community is aiming for net zero by 2040. So that's the first opportunity. How do we work to get these greenhouse gas emissions down to 0 by 2040? It's not very far away. The other opportunity is to work with these industries, some of whom most of them are actively working to reduce their own carbon dioxide emissions, but there will be some recalcitrant ones that are really difficult to remove, and agriculture may be able to offset those emissions from other industries. Back to these gases. So these are the greenhouse gas emissions from UK agriculture, from DEFRA. So unlike all those other industries where carbon dioxide is the principal gas that's being emitted, in agriculture, it's methane, carbon dioxide equivalent, it's methane. So where does methane come from? From livestock, for the ruminants, I should say, from the bacteria living in the rumens of ruminant animals, degrading peatlands, especially when it gets drained and is drier, and manures and manure management. So methane is a significant emission source from agriculture. So is nitrous oxide. And I think I mentioned to you that nitrous oxide is 300 times more powerful as a greenhouse gas over time than carbon dioxide. And that's related to our fertilizer use and soils. And actually, carbon dioxide is only about 10% of UK agricultural emissions. It's things like fuel, heating, energy costs. So there's the challenge. And what can we do about this over the next few years? So I'll take these gases one at a time, nitrous oxide, then methane. So nitrous oxide, this graph on the left-hand side shows the typical greenhouse gas emissions from some work done by ADAS on the Reducing Nitrous Oxide Emissions project. So this first column is the emissions from winter wheat, broken down into various aspects of winter wheat growing. This is winter wheat grown for things like biscuits and for feed for animals. We've got milling wheat here, grown for bread. So this dark blue line is the use of fertilizer. And so you can see that fertilizer is a significant source of greenhouse gases, including nitrous oxide, also carbon dioxide here. And then here, look, soil nitrous oxide emissions related to fertilizer. The soil is a complete soup of microbial activity, air, water, creatures, and they're all cycling nutrients and elements in the soil. And as part of that vibrant activity in the soil, nitrous oxide is one of the sort of inevitable emissions from the soil. And then the light green is residue related, in other words, the straw, the breakdown products of these crops that we grow and how they are breaking down in soil. So if you look at the carbon footprint per hectare of wheat, you can see that an awful lot of this is related to fertilizer and nitrous oxide emissions from soils. So there are already quite a lot of activities that farmers can work on to reduce this large proportion of emissions from crops. For example, across Europe, fertilizer manufacturers are producing fertilizer now that is, it's called abated. The companies are using best abatement technology to reduce the emissions from their manufacturing process. And so many farmers are now purchasing abated fertilizer so that that first dark blue line is smaller. Secondly, the use of the fertilizer in the soil itself, soil nitrous oxide fertilizer. We can be a lot more precise in the timing and the precision and the amount of fertilizer that can be used. And it's possible to add ingredients to fertilizers to slow down the breakdown and try and time the breakdown of the fertilizer and the availability of the fertilizer to points just when the crop is growing, rather than getting losses at the wrong time of the year. And so we're hopeful that this pale blue line can be reduced. Precision is important, and so farmers are looking in detail at the characteristics of individual fields and examining whether a part of the field might be a lower yielding part or short of a particular fertilizer. And then with technology, we're able to do variable rate fertilizer applications, and so that we can be much more precise across the field. Nitrous oxide from the residues, really a similar scenario of making sure that the residues from crops are incorporated into the soil by earthworms, broken down by microbes, not lost in other ways. But this chart on the left-hand side shows the greenhouse gas emissions per hectare. And so if we can be more precise with our production system, we might be able to get more tonnes per hectare. The same amount of fertilizer and other inputs, like the inputs that protect the crops from competition from diseases and weeds. If we can get 10 tonnes a hectare instead of 8 tonnes a hectare, then the carbon footprint of a single tonne of hectare is less. And so adapting to climate change for agriculture isn't just about reducing rate and low input, for example. It could be about sustainable intensification, being smarter in the field. And Simon will talk more about that. There are opportunities for plant breeding to get varieties that are better at mining the existing nutrients from the soil. And we've got the potential of mapping. So this last picture at the bottom on the right shows one of our fields at the Rice Home campus, actually. The darker the blue, the higher the yield, and the brighter the red, the lower the yield. But you can see around the edges of that field that there are areas that are low yielding. So there could be potential for examining those areas. Is there a reason, like poor soil conditions, or perhaps it's the fact that the tractors turn round at the edge of each field, and perhaps we should look at other alternatives like growing grass or wildflowers in those areas and providing some other ecosystem service. That was nitrous oxide. Just quickly on methane. So methane's principally emitted by ruminants, or rather by the bacteria in their rumens, and also lost from manures. And it's quite exciting, really. There's a lot of work being done on diet and feed additives to see if we can alter the rumen bacterial communities and the amount of methane that's emitted. Making sure that the welfare and overall management is really, really good in order to increase the sustainable intensification, if you like, of the production. I took this picture a couple of weeks ago at Rice Home, where we're lambing at the moment. Now, these lambs will belong to a mother of mothers out of the photo. So supposing one of the mother sheep spends a year emitting methane, producing a single lamb, and the lamb is sold, footprint, the methane emissions attached to that lamb will be the lamb's emissions plus its mother's emissions. If we manage the livestock well and get twin lambs from that mother, then when that lamb is sold, it contains it has embedded in it the methane emissions from a single lamb and half of the mother. So again, that idea of sustainable intensification and very careful resource use is great. We need to improve our manure management, the timing of the manure spreading back to the lands. And there are opportunities like producing biomethane from manure to use as an energy source, so renewable energy sources like this. So all these need careful measurements, and I'm working with Simon and colleagues at the moment at Riceham, starting to look at what is the greenhouse gas and carbon emissions from our farm. Carbon dioxide, that third gas, only 10% of the agricultural emissions. And it's things like the fuel use in tractors, energy use in storage when we're storing grain, storing potatoes, ventilating stores to keep the crops healthy. And so just like in a domestic situation, good servicing of machines, correct tire pressure, good insulation, all play a part there. And renewable energy has an opportunity there. So things like wind and photovoltaics to feed into that energy sector. I did want to mention now some of the opportunities for sequestrating carbon. So as well as improving that carbon trading footprint, things like this hedgerow, there's evidence that we haven't been really recording the value well enough of our hedgerows and the grassy strip that you tend to see next to the hedgerows. It's a very three-dimensional structure. It's capturing a lot of light and storing it in the roots and the fallen leaves and adding to the carbon stock in the soil, the organic matter of the soil, and removing carbon dioxide out of the atmosphere. So that's great. We don't have as many hedgerows in Lincolnshire as in some other counties, but we're understanding more and more that the larger the hedge, if we allow that hedge to blossom, get taller, get wider, it should sequestrate more carbon and offer more biodiversity benefits. So I just mentioned carbon footprinting. What I'm doing at Riceham is something like that. Having a look at the emissions from the system and the sequestration. Are our hedges or trees contributing to anything to sequestration? Are we capturing carbon dioxide and ending up with a net balance? And we are working, this is just an example, but we're working to get the net balance for our farm down to zero by 2040 or before, if possible. There's some interesting technologies that we're experimenting here with. That's a picture of some agroforestry, catch and cover crops, capturing carbon, and meadows and grasslands for capturing carbon, understanding how the grass under our livestock does better. Let me just move on and skip that slide, please. So some of the other work that we're doing at Riceham, looking at carbon capture and storage and sustainable intensification and contributing to the climate change impacts on agriculture, include the work of robotics, which Simon will talk about in a minute. Using state-of-the-art technology to measure the carbon flux, and we're doing this at Riceham. This actually is at our Cosmos sensor, sensing of a range of activities and fluxes in the soil. I'm responsible for this natural flood management area. This is Sir William Worsley visiting an agroforestry area we have. So just a couple of slides on these. This natural flood management, this isn't actually about farming, but the way that the land can be used to mitigate against some of the impacts of climate change, for example, flood. Fortunately, where we're sited at Riceham, we're unlikely to contribute to a flood event downstream, but this is a demonstration that we run at Riceham to see what the potential is. Here's a stream running through the farm estate, and we've installed, hopefully you can just see, little barriers. They're porous and let the fish through, but when we have a flood event, the water is held back and flows out into these side ponds through channels, and that has a number of benefits. Perhaps that takes the peak off the flow and the flood, so it might not go into houses downstream if this was a real system. It slows the flow downstream and gives people time to adapt downstream to the onset of an imminent flood. And then this sort of landscape gives greater biodiversity benefits. The more edge you have around water, the better. It might allow infiltration of these flood events and extreme water events into the soil and into the underground aquifers better. And actually, if I was a farmer, I would be exploring, in the face of climate change, whether I could take the water out of these ponds at high flood water at times when there's no impact on downstream water life, and storing this is on an offline irrigation reservoir somewhere that we could then use for irrigation in dry summers. So this is a really beautiful and elegant case of using farmland to adapt to climate change and provide opportunities for biodiversity and agricultural production as well. The second one is agroforestry. So here, this is it's a little bit hard to see from this picture, but you can see trees within an arable crop. And again, it's a very compelling case that we should be able to capture more light by this sort of system. And the trees could be producing wood or fruit or nuts, plant protein, as well as the crops producing food underneath. And we should be able to get more light capture and therefore more carbon capture through a system like this. It is compelling that we should be able to capture more carbon and store it through this system, but it's going to take additional technology to deal with these obstructions, if you like, in the field. And so using robotic technology to sense the trees and work around them is something that we've got the potential to do in the future. Looking after us, I keep putting this picture up of hedges because they're so important, but looking after our soils, using them as a carbon sink will improve the footprint of the farm. But we also, and so I hope we get to this net zero point and contributing and mitigating climate change and giving opportunities for biodiversity in this process. But then we have the opportunity of working with other businesses. And I'll show you what I have in mind here. Biodiversity net gain is one of these. In the Environment Bill, which will be properly launched hopefully in the next couple of years, organisations like housing developers will have an obligation to address the biodiversity that's being lost, say, on building a housing estate, and offset that lost biodiversity plus 10% on other sites. And so we have an opportunity in agriculture to act as a sort of habitat bank to accept those biodiversity losses and replace them in farmland, woodland across Lincolnshire. And part of that will, in addition, sequestrate carbon. That means we may also be able to store carbon and trade carbon. So we can work with industries that have done as much as they possibly can to reduce their own carbon footprint and are still left with a residual amount. If the UK is to reach net zero by 2050, we can't be left with a residual amount. And so agriculture has an opportunity to sequestrate some of that carbon. And lastly, diversification. We've noticed during the pandemic that there's been a really improved interest in the attitude of everybody towards the countryside and all that it offers, whether it's mental well-being, physical well-being, or food supply. And so hopefully that's going to stay over the coming years, and there'll be opportunities for Lincolnshire farmers to diversify into tourism, sharing what they're doing in terms of carbon sequestration or biodiversity provision, and encouraging staycations, well-being, and getting other incomes from that sort of activity. And secondly, hopefully there'll be a move towards understanding more about the value of local food and seasonal food and less food waste. I'll just pop up there a couple of logos that you may see on foodstuffs. The right-hand one showing that it's been produced in the UK to high conditions, good standards of food production. And the one on the right is Leaf, linking environment and food, another brand label, if you like, that shows that the farmers are doing a lot to understand integrated farm management. And I think that finishes. I hope we will end up, this is my last slide, Simon, we're going to end up with a much more diverse agriculture in Lincolnshire. I believe it's going to be more vibrant. There are going to be opportunities for carbon capture and storage, producing food, dealing with food waste, having smarter technology, which Simon will now explore, tackling the emissions from ruminants, growing energy crops, and having other industries related to energy, renewable energy, plus more wildlife and plus more people enjoying the countryside. So hopefully that's given you a taste of what I believe is ahead for agriculture in Lincolnshire. And I have to say it's one of the most exciting times in my quite long career in agriculture. So thank you, Libby. Thank you for listening.
I'm going to unmute my mic. Yeah, so thanks, Isabel. That's fantastic introduction to what I'm going to talk about. I hope you can see my screen. So I'm Simon Pearson. I'm sort of more going to, as Isabel said, really sort of talk about some of the sort of technology approaches that we are taking to try and solve some of these problems. But all I really want to emphasise is what Isabel said, is that, Houston, we've got a problem here with greenhouse gas emissions from the agri-food chain. So when these data are from the whole of agri-food, so it includes agriculture, the 10% that Isabel just mentioned, but also the emissions all the way through the food chain. So that includes in manufacturing, retailing, delivery, waste, etc. And the greenhouse gas emissions from agri-food are immense, and it's 21 to 37% of all of the global greenhouse gas emissions from the planet. So that's agri-food. So it's a really significant chunk. To put a number around it, it's 13.7 billion tons of CO2 equivalent each year across the planet that is emitted because of agri-food. Now, of course, you can't cut it off because we all need to eat. So it's a really intractable problem, reducing those emissions. And a lot of those emissions are a function of the biology, intrinsic biology of food production itself. So as Isabel mentioned, the methane emission from cows, etc., it's an intrinsic function of food production. So it's a very, very challenging problem. But there's absolutely no doubt if we can't deal with some of the emissions in agri-food, then we won't be able to meet very challenging climate change targets. So it's a problem for all of us that we've got to look at to try and solve. So what are we doing about it? Well, just wanted to highlight just a few things that we're trying to do at Lincoln, and we work in the Lincoln Institute of Agri-Food Technology at Rhizome. There's a bottom left picture of the Rhizome campus. It's a stunning site and location. We share that with Bishop Burton College. It's a 400-acre farm. We operate out of the old Bishop's Palace, which is the building on the right-hand side, which is the old what we call the old hall. It's a grand building. It's a fantastic, iconic building in Lincolnshire agriculture. But what makes these things happen is a team of people. So we've got a significant team of people now operating on this, probably near about 45 people full-time, and then a cohort of about 65 PhD students between now and over the next 8 years. So there's lots and lots of research going on, and it's a fantastic, exciting place to be, with lots of opportunities for everybody. So why have we got a problem? I just wanted to show this this message, and I think that it's now widely accepted that agriculture has to change, and agricultural production is not only impacting the climate, but climate's impacting agriculture. So this is a great example of a John Deere tractor ploughing in incredibly wet soils. It shouldn't be happening, but those high mass machines are damaging those soils, and we see that across the whole of global agriculture. So many of these processes are unsustainable, so not sustainable for the future. So we need to sort of look at a whole new paradigm in how we manage agricultural systems. And what is the climate doing? And the climate, it's giving us a problem. And I just want to show this data. If you just look at the data, and I'll put a ring around the critical bit. But this shows the wheat yields at a famous research station called Rothamsted, which is in Hertfordshire. It's one of the most famous global agricultural research stations, and it's in the UK. And they've run an experiment called the broad bulk experiment, where they've grown wheat on the same field with similar varieties with the same processes for over 100 odd years. So they've got a fantastic data set of what's been happening to our wheat production. And the black line with the crosses shows the wheat yield from the early 90s through to 2019. And if you look at that wheat yield, you can see that pre-2008, there's some variance. You'll see some variance in yield going up and down. But if you look post-2008, the variance is very considerable indeed. And because it's a standard experiment, one of the primary explanations, not the only one, but it's quite it's quite significant evidence around it, that it's climate change and climate variability which is affecting these yields of wheat. So not only we've got a problem with the amount of greenhouse gas emissions that are coming from the agri-food chain, we've also got a problem that the climate is interacting and also affecting the amount of food that is produced. So we've got a double problem that we've got to solve. So it's it really is challenging, and it really is very urgent that we start to think about it. Now, how do we think about it? Well, we're looking at technology, and what I want to do now is really show the timeline of technology in agricultural development, to really put in perspectives the urgency and the timelines to develop technology for agriculture. And I want to now take you back to a journey, and where we're at now is in what's called the fourth agricultural revolution. But I want to demonstrate where we got to on the fourth agricultural revolution, which we're in today. I want to really give you a perspective of where we've come from, so you will really have a clear understanding of the timelines of this development. So we started off in the first agricultural revolution, and that was around 1790, 1810, that era. Lincolnshire was absolutely the forefront of that first agricultural revolution, and it was around new machines, new technologies, new horse-drawn machines. And there's a great example here, what's called Garrett's patent hoe, patented in 1820, and that was state of the art in 1820, and it was a hoe with a horse and one person. Then the second agricultural revolution was around steam and diesel engines. So just as a picture here, this is a tractor steerage hoe around the Second World War. Wouldn't get past health and safety these days, but it was two people actually, one tractor and one hoe, that same size as the horse hoe. Lincoln, as a city of Lincoln, had an incredibly important role in the second agricultural revolution, and that was around steam engines, steam traction engines, and really putting power into agriculture. Lincoln as a city grew largely on the basis of that industrial might of steam, which powered global agriculture worldwide for many years, probably up until the Second World War. Then we hit the third agricultural revolution, and problems then started to occur. And the third agricultural revolution really took off around the Second World War with the introduction of herbicides. So this is the classic one, Weedone, which is the first one patented during the Second World War. And then we've more recently had glyphosate. We've also, as well as synthetic chemicals. We've also had advances in plant breeding, so genetics, which have driven yield, etc. And that's led to a massive expansion, growth in yield, and also resilience of the farming system. There's absolutely no doubt about that. But the question is, are we coming to the end of the road? So it's becoming more and more, people are becoming more and more aware of the dangers sorry, not all dangers, but risk of using synthetic chemicals. We're starting to see yields plateauing off, which I've shown you already. So has genetics breeding, have we started to plateau out, etc. So third agricultural revolution, are we coming to the end of the road? I don't necessarily think so, but certainly we need to step on the gas and find new ways to produce food. Is it going to be through use of things like genetically modified organisms, well, or genetically modified crops? Back 20 years ago, that was seen as a panacea. So one of the things that could solve many of our food production problems. I think there's now a consensus, though, that there isn't a single panacea. There isn't a silver bullet which is going to solve these immense problems of the agri-food supply chain. And whilst we don't have many genetically modified crops in the UK, they might re-emerge. But if they do re-emerge, then we need to think carefully about what we do, public perception, and liabilities for the use of those organisms. So I don't rule them out at all, and I think we'll see some of those perhaps emerging, and I hope I hope we do start to see some of that technology advancing. But how are we going to solve these problems? So there isn't a single panacea. There is not one silver bullet which is going to solve our problems. What we know is, though, that agriculture is the ultimate interdisciplinary skill or job. Absolutely interdisciplinary, and this is why agriculture is such a great place to be. So if you're thinking about careers, it is a wonderful place to be, because agriculture, people think of the farmers. So I've shown this in the box in the center, but if you think of that farmer, well, that farmer's got to be a computer scientist. So you can see the little data stack here. That farmer's got to be a telecoms expert now, because they're sending data all over. Got to be an engineer, these vehicles, might even be using space technology. All tractors now, most modern tractors are GPS guided. They've got to think about energy, the environment, light, how they convert light into crops. There might be a roboticist. They've got to think about how they think about carbon to reduce carbon use. There might be chemists using synthetic pesticides or other things. They might use artificial intelligence. They might use renewable energies, and so on. So agriculture is the ultimate interdisciplinary career, and it's a brilliant place to be. And I think one number of the solutions to these big challenges are going to come from interdisciplinarity. So it's going to be farmers working with people who've got all these skills, bringing these skills to agriculture. It will not be one silver bullet to solve these problems. It's going to be teamwork, and that will be the future of agriculture. What else has agriculture got going for it? Well, it's got incredibly rich natural resources, and there's a picture of Lincolnshire Wolds. It's a stunning place, and stunning industry. The Lincolnshire Wolds, for anybody out of interest, the highest wheat yields in the world. Some of them are in the Lincolnshire Wolds, so they're world record wheats. So we have the ability to grow, to be very, very productive, and grow very, very, very productive crops. And it's part of a vast and complex system, and that makes it very resilient. So it's the complexity makes it resilient. So great examples through COVID. The food system did not collapse. It kept going, and it's resilient because it's complex. And that's good news for anybody involved in this industry as a career, because the whole food system is incredibly resilient. So how do we combine interdisciplinarity with the natural resources and the resilience of the system? How are we going to solve these problems in the future? And there are many technical solutions to the future challenges of climate change and agriculture. We're looking at some of them. We might be using agriculture for carbon capture, so producing bioenergy crops, maybe turn them into biochar to sequester carbon. It's a brilliant idea. So you can grow things like short coppice willow, burn it, and then bury the biochar, and it's permanently sequestered for hundreds of years. So we can use agriculture for that. We might look at agriculture as part of energy systems. So you might be producing energy from land using solar PV or turbines or batteries. So land itself is a natural resource which we can better exploit. You might be producing biofuels, so it might be biodiesel, or it might be biomass for burning, etc., etc. So lots of opportunities around there. There's lots of opportunities in the digital economy, and that's really sort of data-driven technologies. So one of the things that we're trying to do at Lincoln is connect supply chains. So really try to get a consumer engaged in the supply chain so that we can move data or collect data from a supply chain, from farm to logistics to retailer to home, so that people, when they buy food, have a better understanding of the environmental cost of their food and can choose food with better environmental credentials over other foods that might not have those credentials. So you've got the consumer using data to drive choice. We've got lots of work going on with sensors, sensor technology to monitor the environment, monitor crops, etc., etc. But it all comes back to the fact that there isn't a single panacea. Now, what we're doing at Lincoln, where we specialise, is on robotics. And this is the fourth agricultural revolution, and this is where we're at now. So we've been through those three agricultural revolutions. We're now on the fourth agricultural revolution, and it's around robotics, AI, and use of data. And it's otherwise known as the digital agricultural revolution. And this is what we're trying to lead out at Lincoln. And these are a couple of the robots, and just show you the pace of change. So the first weeding robot was actually invented by these people called Tin and Haig, 1996. It's also in the UK. And the absolute state-of-the-art robotic systems now are built by a company called Garford's, who are in Lincolnshire. And this is a picture of one of their machines in 2020. And that is a vision-guided hoe. So rather than using pesticides, there's a camera on the front of that vehicle. I can just show it here. There's the camera. That's imaging the weeds, and then these hoes are camera guided, and they rotate around the lettuces. And so you're controlling the weeds without the use of synthetic pesticides. It's a huge step forward in the way that we produce vegetable crops, and that is a Lincolnshire company who we're helping. Robotics, though, will have quite an impact, and this just shows some of the work that we're doing on robotics at Lincoln. We're working on a number of crops. We've been specialising on soft fruit, and we work with a company called Sala Robotics and Berry Gardens Growers. And where we see a future in the fourth agricultural revolution is families of smaller scale robots. And this is a robot called Thorvald, who has developed, where the hardware was developed in Norway by Saga, and then the software for this, the AI, the control for it, was largely developed at Lincoln. So we see a future where you might have a fleet of smaller robots rather than that heavy John Deere machine, which I showed earlier. And this just shows the robots moving around some fields. We've got a number of these now at Lincoln. That robot weighs about 150 kilos and it's got battery life about 8 hours. Got very, very advanced autonomy, so that robot can work around the environment on its own. And this just shows the autonomy working. The top view of the pane shows what the robot sees, and then the bottom shows what the robot's actually doing. So the the control system in that is very, very sophisticated indeed. If you have autonomy, you can do different jobs. So this is autonomy in a greenhouse setting, similar robot, and we're using UVC here. That's a completely friendly way to control plant diseases. So you dose UVC instead of pesticides, and that controls powdery mildew. And we've now got these robots working in Kent in farms. 8 robots working this week in Kent, treating fruit with UVC instead of pesticides. There's big experiments going on this year. And that autonomy stack is now very, very robust. If you've got autonomy, you can do other things. You can help pickers. So rather than carrying heavy weights, you can send robots to and from those pickers, and that drives productivity. And this shows another example of using the robot as a fruit carrier. This picker here has got a mobile phone. When they're picking, they call the robot, and we're going to show you a quick video now of that test in Kent. And here you've got a couple of pickers picking across the fruit. Here they are, they're moving along. They're going to call the robot in a second, and then the robot will autonomously come along, take that fruit away, and save those workers lots of time and effort moving heavy weights. So there you go, there's a robot, there's the robot. So that's working in Kent, and all of these technologies have been developed at, or largely developed at Rhizome. We've got a robot fruit farm at Rhizome, and this just shows a picture of it. And we're working on picking, and here's a fruit harvester, which is quite a sophisticated level of control. Here we go, it's picking, it's a cut picker. And then we're looking at how you reduce food waste. So a lot of carbon emissions are because you waste food. If you can predict when a food is going to be ready and sell it to match supply and demand, you will reduce waste. That reduces carbon emissions. And to do that, you need an image system. And this is an image system developed by a PhD student at Lincoln. And what you can see, you can image each individual fruit, and it even gives you the mass of each individual fruit. So if you've got the mass of the fruit, you can predict your yield. And that's the level of the technology that's going on. And we can image every one of those fruit in 3D, and we can image the farm in 3D. And then just to close up, I'm now going to show you a clip from Countryfile, where we challenge Countryfile to count fruit faster and better, more accurately than our robot. And this is an image.
The first one will be fruit counting. What we're going to try and get you to do is count faster and more accurately than it can.
So how does it count the strawberries? What is it looking for?
Yeah, so we use vision. It's going to use this camera right there, looking at the row, and it's going to detect the position of the ripe and unripe strawberries.
This space tech strawberry counting race is on. It's time for me to pit my wits against this robotic rival. 3, 2, 1, blast off. The fruit count is on, and I'm giving it everything I've got.
So that was a short clip from Countryfile where we challenged the presenters, and we beat them. But it's also, I just wanted to show that because that is a technology of the future, reduce food waste, that will help the climate scenario. But all that work was done by one PhD student, Raymond Kirk. And the pace and the excitement around that technology is fantastic. So if anybody wants to get engaged, please shout, because it's a great place to be. And then my final slide, though, back to the agricultural revolution. Robotics is going to be the fourth revolution, and we are advancing at pace. And this just shows our robotic hoe. So we've got this hoe on a robot platform. You can see it looks very, very similar actually to the hoe on this horse. This robot is 2 horsepower, so it's 2 of these 1820 hoes. And our next challenge is to scale it, and these things are scalable. So you can either scale it through lots of machines, or you can have a slightly bigger machine. So we're looking at scale at the moment, but these are the technology we think are the future. And I pose my last point is, here we are, we're in the 4th agricultural revolution. We are seeing it now. It's happening today. And I think back in the 1st agricultural revolution, people didn't know it was happening. It took 50, 100 years for these things to evolve. but we're seeing it today, and it's happening very, very fast. And I think what the exciting thing is that I ask, what does the future look like? Nobody knows what the future looks like, but we have to keep going because we've got a massive problem, and that is decarbonising agriculture whilst securing food for all. And that is a big problem of today, and it's a big problem of now. So that's it. So thank you very much for listening. And I think Isabel now come back in. So there you go. So thank you for listening. What I'd ask anybody who's listening, please post your questions in the chat, and we'll try and handle them over the next few minutes. So I'm going to ask Isabel a question, and perhaps she could do one.
I've got one for you. Come
on, Isabel. So what's the future? Can you answer my question then? So what do you think the future look like? I know you've mentioned it in your talk, but what's if you're in a space machine and you could go into Lincolnshire in 50 years' time, what are you going to see?
Yeah, well, I think what's really good is that currently we know that the way we farm is not sustainable. We're producing pollution that impacts on the atmosphere, water, soil health, biodiversity, and I think we're going to resolve all of those challenges. And so we'll be busy producing food on the best land, potentially quite intensively, but with hardly any sprays. I think sprays are a thing of the past that we'll look on in 30 years' time thinking, why on earth did we spray pesticides all over fields? Because we'll be using robotic technology, perhaps solar powered, totally autonomous, looking after the crops, scouting for pests and diseases, making decisions that are then implemented using technology that doesn't involve chemicals or any damage to anything. We're very aware of the biodiversity that's there and are able to protect it, and we understand more about enhancing biodiversity, because we haven't just got to stop the decline and hold it at a low level, we've got to put it back up again where it used to be. So we do lie in quite a low-lying county, and so there might be some more challenges around saline farming up and down the coast. So we do have some research at Rise Home looking at how to embrace or combat those challenges. So we've got a pan-European project looking at crops that have the potential to be tolerant of those sorts of situations. So yeah, very different. Lots of people, hopefully.
Yeah. So before we go to there's quite a few questions coming in the chat. So what's your question for me then, Is? So then we'll go to the chat.
How soon do you think we'll have electric tractors?
Oh yeah, quite quickly. So we've got quite a significant project which is being run by Mini Sage in engineering, which I'm involved in, to create some of the first electric vehicles for agriculture. We should have the first prototype in July if all goes well. It's a long way, there'll be 2 or 3 years before that gets into industry. I think there's quite a lot of challenges around it, but it's going to happen quick. So 4 to 5 years, all I can tell you, and I can't tell you too much, it won't look like a tractor.
There are still machines that have to be out there carrying the crops in, the potatoes or the cabbages, but bringing them into store. So there still have to be some kind of machine to do that.
And I think the critical thing is agriculture does need power because of the physics. So it won't be lots of small robots. You might have small robots like I've shown for weeding and stuff like that, but the physics in agriculture are very significant. So ploughing, tillage, those sorts of things. So you're going to need power. You won't need the power that you need in a big diesel 120 kilowatt engine John Deere, but it'll be something lower than that, and hopefully those will be lighter weight, so less soil compaction and things like that. Yeah. They'll come really fast. So it's a really exciting area.
Yeah.
Right.
Some questions coming in, Simon.
Yeah. So I'm gonna ask. I'm gonna take Bob's question first for you. Is that all right?
Yeah.
So Bob Mortimer, a good question. So thanks, Bob. He says farms all have large buildings and large roofs. How many farms are using solar panels to generate their own electricity? and more than their own electricity. So are they contributing electricity back into the grid? What's the use of renewables like in farms in Lincolnshire?
Yes, that for me. Yeah. I think that a huge number of farmers have installed PV arrays on their roofs, on south-facing roofs. Sometimes it's difficult to retrofit on existing farm buildings because the infrastructure isn't strong enough to support the panels. But I think that are they net exporters? I think at certain times of the year they are indeed net exporters, Bob. Yeah.
I think it's fantastic. I think that if you've got land, you've got a fantastic resource, because you can capture light, that can capture solar energy for biomass, and you can you can also you need land for wind generation, but if you want AD, you need land. So I actually think a big part of the farm incomes post as we decarbonise is going to be around energy. So I think farms are in a really good spot, hopefully. So, right, going to and Bob's just asked another one on he said the county council has banned onshore wind generation, but is allowing exploration for oil and gas comments. If I take that one, so I don't know the situation on oil and gas, so it's not something I'm aware of. All I'd say is I think there's increasing recognition of Lincolnshire's offshore generation capacity, and it struck me there's a Viking link coming in from the EU. You've got the new links coming in from the Hornsea plants. They're coming into Bicker in Lincolnshire, and I think I worked out that there's more power coming into Bicker than the Sizewell B nuclear power station. So in a field in Bicker. So we've got these amazing natural resources. I think if Lincolnshire can exploit our offshore to get more onshore development, we're in a really good place. And you think of the future hydrogen economy. What's it need? It needs green power. So offshore wind. So I think Lincolnshire's in a good place. Hope that's okay. I'm going to go to Luke, and one for Iz. What about more efficient ways to produce food? Warehouses, hydroponics, vertical farms, reducing need for chemicals, most damage in a physically more controlled, efficient environment. What do you think about vertical farms?
Yeah. So it's a good point, Luke. So the lovely thing about agriculture is that it harnesses the sun's energy, which is free. And the minute that we put something indoors or stacked, we have to address that light in some way. And that's with the LED technology, that certainly is a lower cost and less hot cost. We used to have to do a lot of cooling prior to LED. So you're right, there are roles for vertical farming, stacked systems, using redundant buildings in cities and on farms. So I think it has a part, but we have to be a bit careful. We're still learning the technology to ensure that it really is carbon footprint wise, just as good a solution as an outdoor system.
Yeah.
Certainly more controlled.
Yeah, I agree. And then I'm going to go to you again, Rebecca, then I'll answer Peter's questions, if that's all right, Peter Williams. But Rebecca Forster's question, how will new funding mechanisms facilitate carbon reduction in agriculture and perhaps widen accessibility to the cutting edge technology that's been introduced?
Well, I'm very aware that the agricultural, there are going to be funds to help farmers who often have the first bright ideas to innovate and work with organisations like universities to develop more research into cutting edge technologies. And Simon, you'll probably have an angle looking at it from a university perspective, looking at research and introducing new technologies. That's probably similar, lots of opportunity.
Yeah, exactly. And the Farm Investment Fund's going to support infrastructure developments, and I think robotics are in scope. So I think as CAP changes to ELMS, there'll be a focus on carbon, but also within the CAP changes, I think farmers will be supported in trying to buy some of these new technologies, which is, I think it's good news.
It slightly ties into your point, Peter, that are things affordable? Sometimes we need government interventions and policy to drive new technologies that don't make financial sense until the technology is established and then becomes cheaper, which I think slightly picks up on your points about wind and solar, that sometimes these things need driving with policy to get them off the ground.
Yeah, and then just to close out with Peter's point, I'm just conscious of time, but lots of international collaboration, Peter, on this, and national collaboration. So our Centre for Doctoral Training is with Cambridge and UEA, and if anybody wants to connect into us through that, please do. That's 50 PhDs through the EPSRC, and lots of international collaborations too. So it's a global challenge. We are. The good news is we're not on our own, and we're working hard to collaborate to solve some of these problems. So I think we're now timed out, actually. I think we've gone a little bit over time, so I apologise to everybody. I don't think we've been cut off. But Isabel, thank you so much. Terrific as always. And please, if anybody wants to reach out, get in touch with us. Please do, just send us emails, connect to us. I just really, agriculture has got a massive problem. We're all really engaged in this problem, and we've really, really got to solve it, and we'll solve it together. And for careers and future opportunities, please shout out. It's a great place to be. It's fun, it's engaging, and it's moving at a terrific pace. So without further ado, thank you very much.
Thanks. Bye, everybody.